Hey everybody, Mr. Judson here. Well, June has finally arrived. I guess we're getting close to the end of this. We really only have one more thing that we need to learn that's really going to help us with this idea of a ship that goes out a certain distance at a certain bearing and then changes course, and how far is it from port. We're going to try and make those problems a little bit easier. And so what we want to do is we want to talk about something that's called vectors. And because this is new to us, it's there's a lot of beginning information, but it progresses rapidly. And so what we're going to try and do is make those problems with ships and airplanes a little bit easier. So first of all, what is a vector? And a vector is something that shows magnitude and direction. Shows magnitude and direction. When we say magnitude, this could be how fast is something going in miles per hour. It could be what kind of a force is pushing on something. And direction, that could be like the bearing of an airplane. It could be the bearing of a ship. We know they do it in different ways. And so how fast is it going and in what direction? And usually a vector is just shown with an arrow like this. And if this was the point P, and this out here is the point Q, we would say that this is the vector PQ. And it starts at point P and the arrow goes through point Q. So this arrow up here is showing the direction that we're going, starting at this point, going through this point right here. Another way that they might do this is they might give it a lowercase letter like V. We could say this is vector V. Doesn't really tell us which direction it's going, it's just we're calling it the vector V. Magnitude could also be like just the length of a segment. If we made it as simple as 2 points on a coordinate system, the magnitude would be the length of that vector. So for example, if I had a coordinate system like this, and let's say I had a vector that starts right here at 0, 1, and let's say it goes through the point 3, 2, which would be right about here, and we wanted to find the magnitude of that vector. What we're really talking about is the length. And so if I call this vector A, its length, I would just do the distance formula to figure that out. Now let's say I have another vector that starts down here at 2, -1. That vector goes out here to 5, 0. Well, these two vectors are actually parallel to each other. Think about the slope, rise over run. We're going to go up 1 and over 3. Right here I'm going up 1 and over 3. So they have the same slope, therefore they have the same direction, because they're parallel lines. And if I do the distance formula for each of these, 1 squared plus 3 squared, that's the square root of 10. That's the length of each of these. Okay, if you wonder what I just did, I'm thinking of a triangle like this where this is 1 and this length is 3. Same thing here, this is 1 and this is 3. So if I did the Pythagorean theorem, I'd get the square root of 10 for both of those. So they have the same length or magnitude, and they're both going in the same direction. So therefore we would say that vector A is equal to vector B. Any vector that has the same magnitude and direction, they're considered equal to each other. So if this was my television set in the classroom and I just drew this, I could grab a hold of this and drag it anywhere, as long as I don't change the slope and its length, it's considered the exact same vector. Okay? All right, so here's our first problem. Let's say I've got point P, which is at 3 comma negative 2, and point Q, which is at 5 comma 7, and I want for you guys to find, so these symbols right here, it's kind of like a double absolute value sign. Those double absolute value signs, those mean magnitude. So I want you guys to find the magnitude of the vector PQ, which just really means find the length or find the distance between those 2 points. You guys go ahead and try that real quick. Okay, so you could plot these 2 points and draw a triangle, and then go ahead and do the Pythagorean theorem. That'd work. Or if you remember the distance formula, distance equals the square root of x2 minus x1 squared plus y2 minus y1 squared. You could do it that way as well. Okay, so 2 different ways. I always like pictures. I think seeing it makes it a little bit easier, so it makes sense to me if someone uses that. But this is quicker, and so that makes sense as well. So the magnitude of this is going to be the square root of 5 minus 3, that's 2 squared, plus 7 minus a negative 2, that's 9 squared. So I'm going to get the square root of 4 plus 81, which equals the square root of 85. There's my magnitude. All right, this idea is going to be something that's real important to us. Component form of a vector means it starts at the origin and goes to a certain point. And so what I would do is I would write something like this. Vector v. By the way, I don't know why this happens, but when I was in school, I learned that you always put this little arrow above a letter to show that it's a vector. Our book doesn't do that. What they do is they put a bold letter. It's a bold lowercase letter without this arrow. Sometimes they do put the arrow in, but sometimes they don't. So just so that you guys are aware of that, a bold lowercase letter means a vector. So if I say that this vector equals, and then I put 3 comma 5, and I've got these sort of greater than, less than signs for brackets, that's component form. And what it means is vector v starts at the origin and it goes to this point. So in a picture, this vector starts right here at the origin. 1, 2, 3, 1, 2, 3, 4, 5. It goes to 3 comma 5, and there's what that vector looks like. This is vector v. And so this is an important idea to us. We want to make sure we understand this, and it's going to help us solve that airplane and ship out at sea problem. Okay? So if they ask us to find the magnitude, so here's my double absolute value signs, the magnitude of vector v, well, if you think of the distance formula, here I've got 0, comma 0. Here I've got 3 comma 5, and if I do x2 minus x1, it's really just 3, and then y2 minus y1, it's really just 5. So the magnitude is really equal to the square root of 3 squared plus 5 squared. So that would be the square root of 9 plus 25, which would be the square root of 34. So if we wanted to make a rule, we could say if vector A equals, in component form, x comma y, then the magnitude of vector A is equal to the square root of x squared plus y squared. That's an important piece to us right there. Okay? the magnitude of any vector when it's in component form is just equal to the square root of the x-coordinate squared plus the y-coordinate squared. All right, so let's say we had a problem like this. They want us to write the vector PQ. So it starts at point P and goes through the point Q. So this is where the arrow's at. In component form. Now you guys might look at this and you go, well, wait a minute, how can I write that in component form? It doesn't start at 0, 0. But remember, once you have a vector, you can move it anywhere in the coordinate system, and as long as you don't change the length and the direction, it's considered an equivalent vector. So if I move this to the origin, where would that have moved to? That's the way you want to think about this. Why don't you guys try that, okay? Remember, pictures are always helpful. Draw a picture of what you know. Okay, so if I draw a picture first, let's see, negative 3 comma negative 2 is right here. 5 comma 1 is right here. And there's the vector we have. This is point P, this is point Q. Negative 3 comma negative 2 and 5 comma 1. So if I want to write this in component form, that means that the vector PQ is going to equal some xy coordinate where I'm going to put these less than, greater than signs in there, but I want it to start at 0, comma 0. So when you plot points, you know, we start at the origin and we go this direction along the x-axis, and then we go up a certain distance. So what I want to know is how far am I moving all the way over to this point, and then how far up am I going to get to this right here. And so the length of this segment, I could just count, start right here and go 1, 2, 3, 4, 5, 6, 7, 8. But I kind of like to have a quicker way to do that. And so when you want to know the distance between two numbers, so in this case two x values, how far is it from negative 3 to 5, you do the larger number minus the smaller. So 5 minus a negative 3 means 5 plus 3, that's 8. And how far is it from negative 2 up to 1? Well, 1 minus a negative 2, that's 1 plus 2, which is 3. So if this point was at the origin, I'm going over 8 units and up 3, and so there's that vector in component form. And it's real important that we remember this. Let me put some more tick marks here. That'll be 6, 7, 8. 1, 2, 3. If I start at the origin and I go out to the point 8, comma 3, this red vector here is equal to the black vector because they both have the same length, which is the magnitude, and direction. They're parallel to each other. So no matter where you move that to, they're considered equivalent. So the vector PQ, which starts at negative 3 comma negative 2 and goes to 5 comma 1, is equal to a vector that starts at the origin and goes to 8 comma 3. It seems like kind of a simple idea, but it's a really important idea for us to get. Okay? That vector and that vector mean the exact same thing, because vectors tell us magnitude and direction. What's its length and which direction is it going? And since it's the same for both of those, they're considered equivalent to each other. Okay? So let me give you another one. Oh, I guess if I back up just for a second, could I have done this without this picture? And the answer is yes. The vector PQ, so PQ in component form is equal to x2 minus x1, comma, y2 minus y1. And it is important to know where do you start and where do you go to. The point P is x1 comma y1. The point that you go to, that the arrow's at, is your x2 comma y2 point. So you want where you end minus where you began. And if you just do this right here, you could do this whole problem without drawing a picture. So let's try this one. We still want to write our vector in component form. This time I've got A, which is at 4 comma 2, and B, which is at -3 comma 5. And so we want the vector that starts at A and goes through B, we want to be able to write that in component form. You guys go ahead and try it. So if I just do -3 minus 4, that's -7, and 5 minus 2, that's 3. There it is, done. Didn't even have to draw a picture. Now, I think sometimes a picture kind of helps us understand and makes things a little more clear. So let's just draw this picture real quick. So 1, 2, 3, 4, comma 2, that's right here. That's point A. Point B is at -3, 1, 2, 3, comma 5, 3, 4, 5. So right about here. And what's that vector right there going to be called? If you start at the origin and go the same direction. Well, if I look at it right here, I'm going back. Let's see, we were at, let me write down the coordinates. This was 4 comma 2. This up here is at -3 comma 5. So I'm going from 4 back to -3. That means I went this direction 7 units, and that's in the negative direction. And then from 2 to 5, I went up 3 units. So if I would have started at the origin, and I went 1, 2, 3, 4, 5, 6, 7, and then up 3, that would have put me right there. So there's the vector -7 comma 3, and that vector looks the same as this one right here. It's got the same magnitude and direction. All right, so the last thing we want to talk about here is adding vectors. I love this stuff because I see where all this is going. You guys don't see it yet, but I see how easy it's making the problems that we've done, especially if you go all the way back to chapter 4 and you think about, you know, ships out in the ocean. They were pretty complicated. We made them easier with law of sines and cosines, but we're trying to make them even easier now. Okay? So adding two vectors together. And some of you may have had physics and learned some of this already. Here's an xy axis, and I'm going to call this vector A, and I'm going to call this vector B. Okay? When you add two vectors together, there's a rule that says they have to be head to tail, right? So if you think of this as an arrow shooting through the air, this would be the head, this is the tail back here. Okay? So right now these two vectors are tail to tail. They have to be head to tail to be able to add those together. And remember, I can take vector B and I can move that anywhere I want as long as I don't change the length and the direction. It's considered an equivalent vector. Well, what I want to do is I want to just slide vector B up to here So that's still vector B because it still has the same length and direction as this one down here. They're parallel to each other, okay? And I didn't have to move vector B. I could have slid vector A over here. It would have ended at the same spot. What you get is kind of a parallelogram, okay? And your answer is the vector that starts right here and goes to this point right here. You can kind of start to see it. If a ship has a certain bearing and it goes a certain distance and then changes course and goes a little bit farther, how far is it from port? So you kind of see that stuff starting to develop here. All right. So what we want to do is we want to say that this red vector is vector A plus vector B. So let's say that we have vector A is x1 comma y1, and let's say that vector B is x2 comma y2. And notice how I wrote these in component form because they start at the origin and they go to a certain point. Well then, A plus B is just going to be, in component form, x1 plus x sub 2 comma y1 plus y sub 2. See, to figure out how far out this red vector went, right here, I want to take the x value for vector A, which goes to about right here, and whatever the x value was for vector B, see that's up here, I'm just adding those two together. Here's my x sub 1, here's my x sub 2. When you add those two x coordinates together, you figure out what this x coordinate right here is. And same thing with the y coordinates. I've got a y coordinate right here. Whatever this y coordinate is, as you go across, that's the same distance up. So I've got this y value plus this y value. That gives me the y coordinate at that point right there. All right? So if I had something like this, let's just say that vector A is equal to, I'm just going to pick something that makes sense here. Let's just say 2 comma 4, and it's in component form. And vector B is, let's just call this 6 comma 1. And I want to know what A plus B is going to equal. Well, then A plus B is equal to, in component form, 2 plus 6 is 8, 4 plus 1 is 5, and there it is. And if I want to know what's the magnitude of vector A plus vector B, then that's just the square root of A squared plus B squared, which is the square root of 89. Just kind of think a little bit in your head. If this would have been a ship going out to sea and then it changed course, think of how easy we just found the distance from where it started to where it ended. We just added the x coordinates and the y coordinates in component form, got that vector, and then did the square root of x squared plus y squared. That was pretty simple. All right. One more thing. What if I wanted to find the direction of this red vector? Well, I know that I've got this triangle. Here's my xy axis. This triangle now goes out 8 units along the x-axis and up 5 units. I should be able to find that angle pretty easily, right? If I just say that the tangent of theta equals opposite over adjacent, and then theta equals the inverse tangent of 5/8, then I could figure out what that angle is, and I know the direction of that vector. Alright, so second tangent of 5 divided by 8, I get about 32 degrees, 32.005. There's my direction. And I could adjust this and turn it into a, if it's a ship, it's a north so many degrees to the east. We could work with that from there. But if I'm just measuring from the positive x-axis, then that's my direction of that vector. So this would not apply to a ship or an airplane, right? Because they would start at north and rotate. All right, let's try one more, kind of like this. I think I'm on number 4. Vector u is equal to 4, 1. So it starts at the origin and goes to the point 4, 1. Vector v is equal to the vector 2, 4. And I want you to find the magnitude and direction of u plus v. You guys go ahead and try that. Alright, so u plus v is equal to, in component form, 4 plus 2, that's 6. 1 plus 4, that's 5. If I'm trying to find the magnitude, then the magnitude of u plus v. By the way, something else that's real common with vectors is we say that this equals vector r, which r stands for result. In physics they call it the resultant, but I just think of it as it's our result. So once we know the result, then we could say that the magnitude of vector r is equal to the square root of x squared plus y squared. And the direction, I could say that theta is equal to the inverse tangent of y over x. Right? Remember, tangent equals opposite over adjacent. So these are two really important ideas to us. All right, so I just added the vectors together. So what's the magnitude of that result? The square root of x squared plus y squared, that's 36 plus 25, which is the square root of, 61? And what direction is it going? Well, theta equals the inverse tangent of, so our result is the vector 6, 5. So when I do inverse tangent of y over x, I want to make sure I use these numbers here. So 5 over 6, grab my calculator. So second tangent, 5 divided by 6. And I got 39.806 degrees. So there's my magnitude, there's my direction. So hey, just one quick heads up. Important lesson tomorrow, because we're going to take this information and apply it to airplanes and boats. But on Wednesday, I will not be able to prepare a video for Thursday. My wife is going to have her final surgery. You guys are aware of what's going on. And so we have to be at the hospital at 5:15 in the morning. So I'm just not going to have time to do things on Wednesday. Tomorrow on Tuesday I'll prepare Wednesday's lesson, so we'll be fine for that. But on Thursday I won't have anything. So I probably will just put together some kind of a review worksheet, because by then we will have learned everything that we're supposed to learn. And so I'll just prepare a review worksheet or have some kind of a review assignment for you guys for Thursday. There won't be a video with anything new on it. All right. Also remember, our Central Washington final exam is on June 16th. on a Tuesday, not June 14th, which is a Sunday. So we've got this week and next week. I know I just saw an email put out by B-Ray about returning books and things. You know, if you're taking the Central Washington final, which is only those who signed up for Central Washington credit, you know, we're going to have to work a little bit longer here, but it's worth it. In the end, you guys stuck through, you've earned those college credits, and you'll be happy you did that. You'll look back at this time and you'll be thankful you put in that hard work to get those credits. All right? One more thing that I just want to look at. If you have a vector, let's just say vector u is equal to, in component form, 3, 7. Okay, starts at the origin, it goes to the point 3, 7. Then there's a rule that says if you multiply a vector by a number, in the physics world they call them scalar multiples. Okay, so I think our book will use that word as well. K times vector u is really equal to k times the x coordinate, comma, k times the y coordinate. So if I said what's 3 u, well, that just means multiply these by 3, so you get 9 and 21. It means that this vector is 3 times as long as this vector. Okay? We also didn't talk about subtracting vectors. So what if I say that vector u is equal to 1, 4, and vector v is equal to a -3, 2. And how do you subtract those vectors if you're going to write your answer in component form? Well, the same way you would add those. You would just say vector u minus vector v, so 1 minus a -3, that would be 4, and 4 minus 2, that would be 2, and there's that vector in component form. Okay, so multiply a vector by a number and subtracting vectors. If I had something like, what's 2v minus 4u? Okay, that just means multiply vector v by 2. So I've got, in component form, I've got -6, 4 minus, multiply vector u by 4, that would be 4 and 16. And now subtract those. So a -6 minus 4, that's a -10. 4 minus 16, that's a -12. I now have my vector in component form. If they ask me to find the magnitude of this, square root of x squared plus y squared. If they ask me to find what direction, theta equals the inverse tangent of y over x. Alright, so we just need to get those 2 extra pieces. If you multiply a vector by a number, you multiply both pieces by that number, and subtracting really is just the same as adding. Okay? Alright, here's our assignment. Alright, here we go. We are now on number C20, page 456. We're going to do 1, 5, 6, 11, 17, 18, and then 21 to 23. Alright, there it is, you guys. Have a good day. Stay safe. I'll see you tomorrow.